axioms of real numbers, the foundation of real analysis. So, let's start with the basics. What exactly is an axiom? Axioms are the foundational assumptions we accept as true without proof. Think of axioms like the foundation of a building. They are the basic assumptions we accept as true without proof, and they support everything else we build on top of them. On top of the axioms, we'd build our logic, definitions, and then the theorems and proofs that make up real analysis. In more formal terms, an axiom is a statement that we accept as true without proof. Think of these as the rules of the game for real numbers. First up, we have the field axioms. If you have done some work with algebra before, you may have come across them. We will try to briefly explain them here. These axioms define the algebraic structure of the real numbers. They are what allow us to manipulate and solve equations. Commutativity. This means the order in which we add or multiply numbers doesn't matter. Associativity. This means the way we group numbers when adding or multiplying doesn't matter. Distributivity. This connects addition and multiplication. Identities. These are the numbers that don't change other numbers when added or multiplied. Inverses. These are the numbers that when added or multiplied with another number from the same set result in the identity element 0 for addition, 1 for multiplication. These axioms underpin all of algebra on real numbers. Next, we have the order axioms. These axioms allow us to compare real numbers and talk about inequalities. Take the numbers a, b, and c on the number line. Given these numbers, the order axioms allow us to compare them. Trichotomy. For any two real numbers a and b, exactly one of the following is true. A is less than b, a is equal to b, or a is greater than b. Transitivity. If a is less than b and b is less than c, then a is less than c. Addition preserves order. If a is less than b, then adding the same number c to both sides preserves the inequality. Multiplication preserves order. If a is less than b and c is positive, then multiplying both sides by c preserves the inequality. For proper definitions, these are usually stated in terms of another set P, which is a subset of the real numbers that contains all the positive numbers and define the binary relationship less than on the real numbers. Finally, we have the completeness axiom. This is the most important and unique axiom that sets the real numbers apart from other number systems, like the rationals. The completeness axiom states that every non-empty subset of the real numbers that is bounded above has a least upper bound, or supremum, in the real numbers. To visualize this, let's consider the set of all rational numbers whose square is less than 2. By construction, this set is bounded above, but it doesn't have a least upper bound in the rationals, as we already know that square root of 2 is an irrational number. However, when we consider the real numbers, this set does have a least upper bound within the real numbers, which is square root of 2. This is what the completeness axiom guarantees. The supremum of this set is square root of 2, and it exists in the real numbers. This is a key property that distinguishes the real numbers from the rationals. To summarize, the rationals have gaps, and we found one at square root of 2, while the reals include square root of 2, and completeness axioms guarantee that. This is the essence of completeness. Of course, there are many equivalent ways to state the completeness axiom, but this is the most common one used in real analysis. Now that we have an understanding of the completeness axiom, let's briefly discuss why it is so important in real analysis. The completeness axiom is the engine that powers many of the most fundamental theorems in real analysis. Here are just a few examples. Bolzano, Weierstrass theorem. This is a fundamental result in real analysis that relies on completeness. It states that every bounded sequence of real numbers has a convergent subsequence. Intermediate value theorem. This theorem relies on the completeness of the real numbers. It states that if a function is continuous on a closed interval a and b, then it takes on every value between f of a and f of b. Extreme value theorem. This theorem relies on the completeness of the real numbers. It states that if a function is continuous on a closed interval a and b, then it attains its maximum and minimum values. All three of these theorems are proven using the completeness axiom. Without completeness, none of these proofs would hold. So let us summarize what we've learned about the axioms of the real numbers. Axioms are the foundational, unprovable starting rules of a mathematical system. The field axioms are what allow us to do algebra with real numbers. The order axioms allow us to compare real numbers and talk about inequalities. The completeness axiom ensures there are no gaps in the real numbers, which is essential for calculus. These axioms connect to many areas of mathematics and physics, showing their fundamental importance.